Hello and welcome back to a new Cubyz devlog. As you can see, the world has changed a bit in the last 2 weeks. It's a bit more empty now. That's because I started working on some new textures for everything. And I only made 4 textures so far, so the rest is just empty. If I get closer here, you might notice something. All the logs have a different texture. There is no repetition here. It's all looking unique in its own way, yet it has the same shape. Yes, I worked on procedurally generated textures. For the stone here, for example, I tried to replicate like layers of stone, kind of like you find in slate. And what's interesting here is also, if I have a structure on the side, let's look at this white layer here, for example. Up here it touches with the top side, and on the top it continues, and you can see like this cross section. And that's really interesting, I think. That's something that was not possible with the textures approach, or at least it was very hard. I also made the soil, but there's not much to say about that. For a reference, let's take a look at the old textures again. Here's the log, which is very repetitive, especially this feature down here is clearly repeated everywhere. Same for the stone, it's relatively repetitive, it's not that bad. Or not as bad as with the logs, because it's a bit more noisy. Same for the soil. There are other ways to solve this. For example, Minecraft just rotates the stone randomly. And there's also this approach here, which is used for the cobblestone. Essentially, there's 2 different textures that are used randomly. For example, this here has this grey stone in the middle, while this one doesn't. But overall, this attempt is really hard to figure out, because you have to make the texture consistent with another texture, so the sides have to match basically, and that is really hard to pull off. And also, take a look at this stone here, for example. It repeats here and here and here, so it's, while you can do a lot with this stuff, it's really hard to make it look non-repetitive still. And also the common problem, if you look at the side, it doesn't match up with the top. And that on most sides. On one side it matches, but that's just coincidence. Same thing with the stone, by the way. On the sides it has horizontal layers, and on the top it suddenly doesn't have those layers anymore. There's like a different direction of layers, which just doesn't make any sense. At least not to me. So yeah, let's look at the procedural ones once again. What's interesting about the stone, it's actually need to look at some more stone to see it. Let's go here, for example. As you can see, at this point, the layers go from the top left to the bottom right. But if I go down a bit, they suddenly go from the bottom left to the top right. So the direction of the layering is not consistent. And that is something that can also only be done with procedural generation. Anyways, I have one more thing to show, which would be the top side of the logs, but first of all I want to show the implementation. As always, it starts with the search engine. So I type in GLSL, which is the shader language, and then I want some noise function, right? So Stack Overflow link, some documentation that I don't care about, and GLSL noise algorithms. That sounds interesting. Oh, lots of things I can copy paste. Okay, the first one is just white noise, Perlin noise. Perlin noise is relatively slow, that's why I don't want to use it. And down here I have simplex noise, and I specifically want 3 simplex noise. So let's copy this over real quick. One thing I noticed right away, this function is really long, like it's 70 lines for something that I want to do multiple times per pixel, so it might be worth checking the performance first. And I did this using an interesting metric. Normally you just implement it and measure the performance somehow, but I want to show off a different approach. Essentially here I just counted the number of operations, and it turns out to be 400. So, and to calculate performance we have 400 operations per noise function call. I want to call this at least 5 times. Then I have a lot of pixels on my screen. And then I obviously want to draw my screen 60 times per second, at least. That gives us the total number of operations per second. Then I want to divide this by the number of operations my integrated GPU can do. My integrated GPU can do 1 teraflop, roughly, which is 10 to the 12. And in total we get almost 50% used, just for 5 of these noise functions. And that's not going to work. First of all, this is just a theoretical maximum, this 1 teraflop. So in practice this implementation will not hit that, so it will be a bit slower. And also, obviously I don't want to generate just noise, I also want to render the game, so I need to have some room for that, and 8 milliseconds is kind of tight, especially if I have a few milliseconds for my bloom, a few milliseconds for clearing buffers and all that. So this algorithm is not going to work out of the box. At least not performance-wise. So let's take a look at this. The first part seems to be computing what simplex we are in. In simplex noise the space is essentially divided into simplexes, or these are kind of like tetrahedra, and this is calculating what simplex we are in and what the 4 corners of that are. So there's not much I can optimize here, or at least I don't really want to touch that. Same thing down here where the final noise value is calculated. This is kind of essential. We are taking the gradients and the coordinates and dotting them together with some normalization factors, and I don't really want to mess with that. But what's all this in the middle doing? In the end, this entire piece of code here seems to be just producing these P0 to P3. And these are used down here, and these seem to be the gradient vectors. Not sure why they are called P, but I guess we have to live with that. And all of this, as far as I understand, in the simplex noise we need randomized gradients, so I guess all of this is just generating 4 random vectors with 3 elements each. So if I found a different random number generator, then it might be faster. that's why I looked around the internet and tried to make a noise function myself, but making a noise function yourself is kind of tricky, so I decided to go with PCG 3D, which is the fastest thing I found, essentially, for 3D noise at least. And it's kind of heavy, it has lots of multiplications, it has vector additions, vector bit shifts, vector XOR, and some swizzle magic stuff here. So in total it's around 27 operations. And keep in mind we have to do this 4 times, so we are still over 100 operations for this middle part. And I actually measured if this makes any difference, or if this makes it a lot faster, and it does not change a thing, it's about as fast. And I think the reason for this is that integer multiplication is relatively slow on the GPU. The GPU mostly focuses on floating point operations, and the old algorithm, despite having 250 operations, only used floating point operations, and therefore was as fast as this version, which takes just over 100 operations. So I was just about to give up and just use this version and don't care about performance. But then I had an idea. In many algorithms you see like this multiplication term here. There is some initial value, it gets multiplied with some random number, which is an odd number, by the way. This part is important. And you also see often additions and XORs. That's roughly what I learned. So I try to make the simplest thing I can think of. Essentially I have this input vector of 3 variables. I'm multiplying each value of that with a different factor, and then I'm XORing them all together. And here it's important that these factors are different, because otherwise it will have like symmetry planes, symmetry axes, and we don't want symmetry in a random number generator. And in the end I have the seed, and I also multiply this with 1 factor each. And here it's as well important that the factors are different, because otherwise obviously all 3 output values would be the same. That's not what we want. How good of a random number generator is that actually? I wrote a little text, and I don't know if you can still see it after all the compression, but it's pretty random. I cannot see many patterns, so I think it's a good enough random number generator. I haven't done any more testing than this, so it might turn out to be the worst random number generator in the world, but it seems to look fine, so I'm going to take that definitely. One interesting thing to note here, I also said there's often additions in random number generators. What happens if we change this XOR with an addition? Because in this case I could replace this with a single dot operation, which seems to be optimized on the GPU, as far as I heard. So it would be nice if this would work. But it doesn't, it's really repetitive. And this kind of surprised me, that there's like this big difference between the XOR and the addition. Because fundamentally, as far as I know, XOR and addition are kind of similar in a way. Addition is kind of like XOR, but it has carry. So it's kind of similar. I don't know. Anyways. So I now have this random number generator, and I also made an optimized version for basically when I want to have a three simplex noises with the same wavelength but with a different seed. The thing here is I can just shift these values and it will... I don't need to repeat the corner calculation and some other stuff, so this is a lot cheaper than doing 3 calls to simplex noise. Anyways, you may have asked yourself how I actually made these patterns, because it's kinda not obvious how to make patterns like this. So let's start at the simple pattern. This is actually a fractal simplex noise. Here is an example how this would look. It gives like this cloudy patterns, and obviously in the game it's pixelized, and that makes it a little less obvious that those two patterns are actually the same. But that's what's behind this. Also, if you don't know what Perlin noise or simplex noise actually looks like, it looks like these here, like this for example, or like this. This is roughly how simplex noise looks. So anyways, fractal simplex noise is quite simple. You have a high intensity low wavelength part and a medium intensity medium wavelength part, and so on. And in theory that goes up to like, I don't know, 1000, and that goes down to 1. And the factors and the wavelength each grow by a factor of 2 in each step, and that basically overlays different frequencies, and that gives us this nice cloudy pattern thing. The logs are a bit more complicated. For that, it might be useful to first look at a simpler case, so I'll comment a few things out here. So right now I've removed that part is unused, and these parts are also not relevant. So I have one simplex noise which has a relatively high wavelength in the Y direction and a low wavelength in X and Z directions. And let me show you how that looks real quick. Well, quick is not, it's not really quick, but as you can see it gives like these straight lines, more or less. Of course they are not lines, they are a bit wider than lines would be, but it's roughly like a line, vertical line pattern. And that doesn't really look like logs. In logs, what I would want to have is slightly curly lines, so it looks a bit more natural. And that's what I can use domain warping for. Domain warping basically moves the patterns in some direction, but the movement depends on another noise function. So in this case I take this simplex 1 noise function, which has a medium wavelength 8 to 5 pixels. In the Y direction it's has a bit of a higher frequency, so we get more changes in Y direction than we get in X and Z directions. And this domain warp tells me that I warp the X and the Z value by 0.2 and the Y value by 0.05, it doesn't really matter. And let me show you how this looks in my very quick process. And it's actually kind of hard to notice. Let's try a bigger amplitude, so we, well, more domain warp, so it's more easy to spot the difference. Well, that may have been too much for demonstration. Well, let's do 0.3, I guess. So yeah, as you can see, the lines get a bit curlier and they move around a bit, and it feels more like an actual tree because it has like different patterns and all that. And yeah, I also have an additional noise map that has a lower wavelength to add some finer detail and also some randomness. And yeah, as you can see, that's more or less the result we had first, except obviously I changed the factor to 0.3 there. Should probably change that back, because it is quite a heavy change. Actually, is it is it good if I do live coding here in these videos? I'm already at 22 minutes. I don't know, maybe let's do the stone one real quick. Essentially it's the same approach, except I have lines in X and Z direction. That is done by having a low frequency, low wavelength in Y direction and high wavelength in X and Z direction, which is the opposite of what the log had. And here I'm actually applying a very high wavelength domain warping. And I'm doing this because it gives me like this change in slope, this low frequency change in slope, so I get like different slopes at different places in the world. I already showed that earlier where we went underground. So, back to the interesting parts, and that would be the top texture, which I didn't show yet. As you can see, it's not something you would expect to be able to get from a noise function. And I would claim it's really hard to get something like this from just noise functions, because it's really obvious that there was a pattern here. Especially if you look at the border where it literally switches between one color and another. That would be very hard for a procedural generator. And the way I did this is I cheated. I'm just using a 3D texture for that, essentially. The 3D texture essentially has a 0 at the outside and then alternates between 1 and 2. And in the inside I have two relatively similar materials called Oakwood 1 and Oakwood 2. And the only difference is that one of them has a brightness offset and the other one doesn't. And apart from that, it's exactly the same. As you can see. So that is kind of a cheat here in the system. But this is a really important thing, because without this I wouldn't be able to achieve these patterns. And also it allows if you have a case where you cannot represent this with procedural generation, then you can just use a regular texture, 3D texture to be precise. And this will be especially important when it comes to special blocks, like for example the crafting table, where maybe we have some intricate side texture and all that. And also this means that I can combine multiple materials in a single block. So if I, for example, want to have a mixed stone wood block, then I would be able to achieve this by just using one material for one color and one material for the other color. And I think with this I'm actually able to achieve almost as much as the textured system. And that almost is that you can have at most 8 different materials in a single block. So it's not always going to work, but should be good enough, I think. Yeah, that's all I have. I don't know, it's gotten a pretty long video. Already at 26 minutes. Well, tell me what you think about this. Tell me if you maybe have an idea how to make some of these textures better, or I don't know. And yeah, goodbye.